Hello everyone. In this video tutorial, we are going to simulate the desulfurization of naphtha in ASPEN Plus. So this is the composition of naphtha that we are going to desulfurize. It has this sulfur compounds and some alkanes. So the flow rate of naphtha is 3 tons per hour, available at 25 degrees C and 2 bar. It is pumped to 41 bar, and the hydrogen which is available at 41 bar and 25 degrees C. The flow rate is 4.43 kilomole per hour. So this hydrogen and naphtha, these are mixed, and then the mixture is heated to 250 degrees C in this heat exchange number 1. Then the pressure is dropped to 40 bar in a valve, and this mixture is again heated to 350 degrees C in another heat exchanger, and there is no pressure drop in both of the heat exchanger. This mixture is then fed to a plug flow reactor, the temperature of which is fixed at 350 degrees C. There is no pressure drop in this plug flow reactor. The length of this reactor is 20 meter and the diameter of this reactor is 2 meter. So these reaction takes place in the reactor. Here you can see that the hydrogen reacts with this sulfur compounds, and it forms these desulfurized component, this and the hydrogen sulfide. So you can see in every reaction this sulfur is taken by the hydrogen to form the hydrogen sulfide. So this reaction takes place here, and then the products which contains the desulfurized compounds, hydrogen sulfide, some unreacted compounds, these inert alkane, they are not taking part in the reaction. So they are passed, they are actually cooled in this heat exchanger number 3, where the temperature is decreased to 35 degrees C, and then they are passed through a flash drum. The flash drum separate the gaseous and the liquid products. So the liquid product mostly contains the heavier chemical that are condensed, and the gases, we obtain the gases here, which contains the hydrogen sulfide, some unreacted hydrogen, and other gases. So here we remove hydrogen sulfide from this gaseous mixture with the help of lean amine in an absorber, and this absorber has 20 stages, and the pressure is 4 bar. So the hydrogen sulfide is removed from these gases, and the rest of the gases are recycled to the process. Before we recycle them to the process, this pressure is increased to up to 41 bar and the temperature to 110 degrees C. Okay, these liquid products, this liquid product, it is sent to a distillation column where the rest of the gases are removed, and here we get our desulfurizer product. So we shall simulate this process in ASPEN Plus, and we will also carry out some heat integration analysis. By heat integration, I mean, here you can see that we are heating our mixture. We are heating the mixture here as well. However, here you can see that we are cooling our product. So why not that I transfer this heat which I am removing here to this stream. So this stream can also, the heat of this stream can also be given to this stream or this stream. Here you can see that again we have installed a cooler which is actually cooling down our product. So this heat can also be utilized here or here. So we shall see that how much heat can we recover in this process, and how can we actually design a heat exchange network for this system. Okay, open ASPEN Plus. I am doing this in ASPEN Plus v14. However, if you have an earlier or later version installed, you can do this simulation in those versions as well, whether this is version 8, 9, 10, 11, 12 or a later version. So click on new, and then click on metric, select user, and general with metric units. Click open selected template. First we shall enter our components here. So first component is CH4S, Okay, the second is C2H6S. Okay, I have entered the component here, but the name it didn't show the name here, and also there is didn't show the formula here. That means that it has not identified this component. So for this, just click on this find, and here write C2H6S and click on find now. So this is actually this component, this C2H6S1. So double click on this and just click on this add component, and you can see that this component is added here. Okay. So I will also add the remaining components from here. This is C4H8S, C4H8S add. So this, don't click on replace, otherwise if you replace this component, so add. And C12H8S, H8S, so add this component. C5H12, C5H12. So C5H12 is actually, this is a this is actually pentane, so it must be here somewhere. However, you can also just okay, this is normal pentane. Normal pentane 8, and C6H14. Okay, this is C6H14. So this is hexane actually. This in hexane 8. Another is a heptane, C7H14. Just write this -1, so this will be normal heptane, right? Sorry, this is not actually cycloheptane, this is a normal heptane. This is C7H16, right? Normal heptane. Add this C8H18, C8H18 octane. C8H18 and C9H20, C9H20 nonane. So add this as well. And we also have CH4, this methane. Okay, and another component is of course we have hydrogen H2. I'll just write hydrogen here, hydrogen and equal. So this is hydrogen. We have H2 is hydrogen sulfide. Okay, and C4H10, C4H10. Okay, just and this contains C4H10. This is actually butane, so C4H10-1. So add, selected, add, and C12H10, C12H10, add. Okay, and we also have this amine, and this is C14H3N. This is the amine, C14H31N, sorry, H31N. So this is this amine, add it as well. So now we have added all of our components. It is recommended to rename this with these formulas, so it will make the thing easy for us when we actually uh, define when we will be defining our reactions. So right, just this is C4H8 is rename this C12H8 is and I am pausing the video, and please do this further step these components. It will make things easy for us later on. So you can see that I have renamed all these as per their formulas. So it will make the things easy for me when I will be defining the reaction. Now go to the methods, and here select the method filter, select the all, and here select this Grayson model in G. Just click on G and this Grayson model. Okay, run this, and now go to the simulation. So as per our sheet, first I will install a pressure changer pump. Okay, so the Naphta is coming here. This I will call this as Naphta. Okay, and let me just call this S2 or S1, whatever the name you can call this. And this Naphta, and this is actually then mixed here. Let me call this pump, and this is mixer. So another stream is also coming into the mixer. This stream, sorry. And this stream is actually this stream number 3. We just adjust this. This is a hydrogen stream. Okay, and let me specify this stream now. So this naphtha, the temperature of the naphtha, and the pressure and the composition. So this is 25 degrees C. Pressure is 2 bar, and we are given the mass rate. It is 3 tons per hour. Okay, and the mass fraction is given. So this is 0.0069 and the 0.0147, and the composition of this is 0.0104, and C12H8 is this is 0.0545. C5H12 is 0.0943. 0.0943. C6H14, this is 0.1835. C7H16, 0.2845, and this is 0.2298. C9H20 is 0.1214, and there is no CH4, H2, H2S or any other component. So you can see that the total is summation. The sum is 1. Okay, now we have defined the naphtha stream. So just click on this H2 hydrogen stream, and the temperature is 25 degrees C. The pressure is 41 bar, right? And the mole flow rate is given as a 4.43 kilomole per hour, and this mass fraction, this is 100% hydrogen. Just write one here. Now go back to this, just click on view to sheet, and this is the output stream. We just rename this with let me call this as S1, and this is S2, S1 and S2. Okay, now we are going to heat this to 250 degrees C. So another heater. Okay, and double click on, okay, we have actually not specified this pump, so double click on the pump, and discharge pressure is a 41 bar, right? Back to the sheet, and here we want to raise the temperature up to 250 degrees C. Okay, there is no pressure drop, so just 0 here, and then we pass this through a wall where the temperature is let me call this HX1, and let me call this well. So in this well, the temperature, the pressure is dropped to 40 bar. Double click on this, and the outlet pressure is 40 bar. Okay, just run the simulation to verify that everything is working correctly, so you can determine that how much power is required by this pump. Double click on this pump, and go to the results, and here you can see that the brake power is 15 kilowatt. You can also check this in horsepower, so this is 21 horsepower. Now you can also check that how much heat is required here, so just double click on it, and you can click on results, and this is the heat duty in kilowatt, 565 kilowatt. Okay, now this is again heated to 350 degrees C, so just install another heat exchanger. Just click up escape to exit this mode, and call this as a HX2. Okay, double click on this arrow, feed this stream here, and now this is the outlet stream. Okay, here the temperature is raised to 350 degrees C, so I will just write 350 degrees C. There is no pressure drop, so just write 0. If there was, suppose, 1 bar pressure drop, then you would write -1 here. And again, you can run the simulation, and you can check that how much duty is required by the heat exchanger number 2, HX2. So here is HX1, and we also have this HX2. Let me call this as HX2. Double click on this, and you can see this is the power required by the in kilowatt HX2. So again, view to sheet, and now this stream is fit to a reactor. So before installing the reactor, I will define my reactions. So for that, go to the reactions, click on new, and the type of reaction is power law, right? And click OK. So these are the reaction that we are going to define. Reaction 1, 2, 3, 4, and these are the rate expression for these reaction. Okay, this is the rate laws, rate expression, kinetics of the reaction, and these are the kinetic parameters for all of the reactions. K1, E1 for the first, similarly K2 and E2 for the second, and so on. So let me define these reaction inside the ASPEN Plus. So click on new, and let me, this is just reaction number 1. Okay, and so here CH4 is reacts with the hydrogen. 1 mole of CH4, 1 mole of hydrogen. Okay, as per the reaction, as per the rate law, this is exponent is 1, and this exponent is also 1. It produces CH4, and H2S, 1 mole of CH4, 1 mole of H2S, and as per the expression, rate law expression, this is 0.35 and 0.35. Okay, now another reaction, click on new, and here two hydrogen reacts with the C2H6S, one C2H6S. Okay, as per the rate law, this is 1 and they produces CH4, 2 CH4 and 1 hydrogen sulfide. And these are 0, whether you write 0 or you leave this as a blank. So if you leave this as a blank, so it will mean that it will take this as 0, right? And another reaction, here two hydrogens reacts, two hydrogen molecule react with C4H8S, C4H8S, 1 mole of C4H8S. And this is one exponent as per the rate law. The order is 1. Okay, and this is they produce C4H10, right? 1 mole of C4H10 and 1 mole of hydrogen sulfide. Okay, and similarly another reaction number 4, here C12H8 reacts with the hydrogen. Sorry, this is hydrogen. So 1 mole of C12H8 is react with 2 mole of hydrogen, and this is 1 to produce C12H10, 1 mole of C12H10 and 1 mole of hydrogen sulfide. Okay, so now we have added the reaction. Here we need to enter the kinetics of those reactions. So click on kinetics, and this reaction 1 is selected. So here select this. This is vapor. We are reacting in vapor phase, and the K is 0.2, right? E is E1. It is 200, and this is in joule per kilomole, right? So joule per kilomole. Similarly, now select reaction number 2 in the vapor phase. The value of A is 0.3 and E is 600, right? Joule per kilomole. Okay, in reaction number 1, you need to actually change this to this molarity to mole fraction, right? Mole fraction. Similarly, in reaction 2, change this basis from molarity to mole fraction, and define this for reaction number 3. So this is also in the vapor phase, and this is K is 0.4, E is 600 joule per kilomole, and base is mole fraction. And for reaction 4, this is again change to vapor 0.4, 0.5 and 200 joule per kilomole. Okay, now go back to the flow sheet, and here install a reactor, and that is R plug. So install the R plug here. Let me just call this reactor. Okay, and double click on this arrow to feed this to the reactor. And we also have an output stream. So double click on this reactor, and this is a reactor with specified temperature. Now start at specified reactor temperature. So this is 350 degrees C. and click on configuration. So the length of this reactor is 20 meter and the dia is a 2 meter, right? And click on the reaction. So this reaction set R1, add this reaction set to this reactor, right? Okay, now click on this run button to simulate the process. Okay, when the process runs successfully, you can see this this message here: results available. So in the reactor, go to the stream results, and in the stream results, click on this mass flows, and you can see that this component in the feed the rate was 20.7 kilogram per hour, and here in the product it is only 4 kilogram per hour. So that means that almost 75% has been reacted away. Similarly, these components, these sulfur compounds, they have been, there is 100% conversion of these compounds, and these were the innards that don't take part in the reaction. So you can see that the flow rate is the same at the input and the output. Similarly, there was a new CH4 in the input. However, now the CH4 is produced, and you can also check this hydrogen sulfide, right? Hydrogen sulfide. There was no hydrogen sulfide in the feed. However, now we have 78 kilogram per hour of the hydrogen sulfide in the product, and same for these other components. Okay, again, go to this view, click on view and flow sheet, and now we are going to install another heat exchanger, and this heater, let me call this HX3, and we are going to just click on this zoom fit button, so we will be able to see the whole flow sheet, and double click on this HX3. We want to decrease the temperature to 35 degrees C, and there is no pressure drop, zero pressure drop, and this stream is fed to the flash. Click on separator, flash 2, and it will now separate this into the vapor and liquid. So this is vapor and this is the liquid part. Ensure that you connect with the red stream, right? So double click on this, and just it is operating at the same 35 degrees C. There is no pressure drop in the simulation view. Okay, now view and then flow sheet. Okay, just call this flash, flash, right? Flash. Yeah, double click on flash, and flash, where is flash? Yeah, this is, and click on the stream results. So if you click on the mass flows, okay, we have not yet run the simulation, I guess. Run the simulation. Okay, and there is actually no product in the vapor phase. Everything goes into the liquid. So let me check that what is the problem. Then click on view this flow sheet, and double click on this. Okay, actually the pressure is 4 bar, right? So there is pressure drop in the flash drum, because at 41 bar and 35 degrees C everything is still liquid, so we need to reduce the pressure in the flash drum. So this is 4 bar. Run again, and now check the stream results. So now you can see that this is the mass flow rate of the vapor stream, and this is the mass flow rate of the this one is, I guess, which one is the liquid stream? S8 is the vapor stream, right? So S8 is the vapor stream. So now you can see the hydrogen sulfide, almost all of the hydrogen sulfide must be in the, most of the hydrogen sulfide must be in the vapor stream. So Okay, this is only 25 kilogram are in the vapor stream, and the 2 is still in the liquid stream, right? So and you can also see the other this C9H20. So you can see that most of the C9H20, this is in the liquid phase. Similarly, the C8 and H18 is also in the liquid phase. So in the next video tutorial, the next part of this tutorial, we shall separate hydrogen sulfide from this stream, and from this stream we shall recover our desulfurized product. So we shall use an absorption tower here and a distillation column here. See you in the next video. Thank you.